So this is lecture 6, and I'm going to give this a try where you would listen to this lecture at home, and we will certainly discuss it and review it in class. But if this works out, we can save some time and do more MATLAB in class. So the subject of this lecture, lecture number 6, is periodic structures. And it turns out a whole lot of things, electromagnetic things, are periodic. Diffraction gratings, phased array antennas, frequency selective surfaces, a whole bunch of stuff. So what we'll talk about in here is all the math and theory behind this that will let us model periodic structures and understand them from a mathematical perspective. In fact, we're going to use this so much, even if a device isn't periodic, very often we can make the approximation that it is and still get very good answers. So I'll run you real quick through some example periodic devices. Then we're going to dive right into the math describing the periodicity. What the goal is that we can then lump that math into Maxwell's equations and use that to start describing and modeling devices. Next, we need to talk about electromagnetic waves inside periodic structures. There's some very interesting and very simplifying conclusions that we can make. Then that's going to lead into some extra topics we're going to talk about. A little bit about electromagnetic band diagrams, and these are analogous to the band diagrams that you probably learned in a semiconductor class. And we have the same types of bands for very similar reasons with electromagnetic waves. In semiconductors, you have electron waves, if you will, traveling through a periodic potential. Now we have electromagnetic waves propagating through periodic materials. And then that leads into a concept called index ellipsoids that we actually already talked about a little bit, but now you're going to be able to have the beginnings of how to calculate them using a numerical method. So here we go. Here are some interesting examples of periodic electromagnetic devices. We have at the upper left diffraction gratings. So very often they'll use these things in spectrometers. They'll separate wavelengths, each wavelength diffracts into a slightly different direction. Waveguides, a lot of folks are looking at incorporating periodic structures into waveguides to do some really neat thing, to compensate for dispersion, to make the waveguide smaller, to make the mode in the waveguide even bigger sometimes to handle higher power. There's folks working on band gap materials. This is the analog to semiconductors where you could have insulators and conductors. You can have areas of a lattice where waves can propagate and areas of a lattice where they don't, and it looks like a mirror throughout. There's a whole topic of metamaterials. Perhaps we're not happy with the materials that nature has given us, and we want to intentionally build in structures to give them new and probably amazing and really cool electromagnetic properties. And so that area is called metamaterials. Very often in antennas, rather than make one big antenna, we would make hundreds of little tiny antennas and phase them all differently to do some interesting things with the radiation pattern. We can use periodic structures to slow waves down. There are slow wave structures that in principle would stop an electromagnetic wave, but we can certainly slow down an electromagnetic wave so you could literally walk faster than the wave is traveling. Frequency selective surfaces. These are used extensively in stealth. So I have a picture of a stealth fighter there, but it's a periodic arrangement of metallic elements so that when you hit it with a wave, it tends not to reflect. You really just see the background reflection, whatever you would see if the airplane's not there. So what do we mean when we say something's periodic? And there's two viewpoints, and we're talking about one but not the other. The first is periodicity at the atomic scale. If we look at the atomic lattices, we could say that a material is periodic. But this isn't what I'm talking about. I'm talking about much larger scale periodicity, like the devices I'm showing on the right. Very often, for microwaves, you could stick your fingers between those holes. So these are physical features that we intentionally machine or somehow form that would interact with an applied wave to do all kinds of crazy things, as you'll learn. So in this class, when we talk about things being periodic, we're really talking about at the larger scale, where there's There's actual mechanical structures that are periodic in your device. So if something's periodic, we need to start putting some rigor to how we describe that. And there's actually an infinite number of ways that things can be periodic. So we need some kind of simplification or something to do here. So we classify periodic structures. It turns out at the highest level, or maybe I should say the lowest level, the most detailed, there are what is called 230 space groups. So this means there's 230 ways in which something can be periodic. If we make some generalizations to that, we can reduce that down to 32 crystal classes. And the more useful are the ones below that. And these are some of the ones you probably have seen in your chemistry classes, maybe semiconductors. But if we make a few more simplifications, we can reduce those 230 space groups into what are called the 14 Bravais lattices. And then even more general than that, the 7 crystal systems. So in order to classify something that is periodic into one of those categories, we need a series of tests. And these are called symmetry operations, and there's a number of them. We could pick a spot in the lattice, and if we translate to another spot in the lattice, if we see the same lattice again, we would say that it has some kind of translational symmetry. Maybe the region of the lattice we're looking at will rotate 90 degrees or 180 degrees. And if the lattice looks the same again, that means something. Maybe we reflect, maybe we flip the lattice left and right. Does the lattice change? If not, or if it does, then that means something again. And there's combinations of these different lattice operations. So in fact, the crystal systems are defined by a set of these symmetry operations, so that if you perform operation 1, 2, and 3 and end up with the same lattice, that means it's a certain type of symmetry. We're not going to do that in this class, but I wanted to mention that there is actually methodology behind classifying these. As I mentioned, 230 space groups. We aren't really going to work with that. We're going to talk more in terms of what are called the Bravais lattices and crystal systems. I think these are all going to be words and titles that you're familiar with. You may not have heard Bravais lattice, but I think the names of the Bravais lattices you may have heard along the way somewhere. The simplification here is we can make something periodic out of triangles, out of spiral structures, etc. To call it a Bravais lattice, we're going to assume that it is a collection of spheres. And if it's not, a lot of times the analogy still holds. Instead of an arrangement of triangles, we'll say it's an arrangement of spheres. But anyway, if we can just say we have an arrangement of spheres, all of these 230 space groups reduce down to the 14 Bravais lattices. And we can also then divide it also into 7 crystal systems, as you'll see. That's the next slide. So here are the 14 Bravais lattices and the 7 crystal systems. So the crystal system are the capital letters: cubic, tetragonal, orthorhombic, monoclinic, triclinic, trigonal, and hexagonal. And then within those we have different things. For example, in the cubics, we have simple cubic, body-centered cubic, and face-centered cubic. And so if you add up all those subcategories, you'll get a total of 14. So those are the 14 Bravais lattices. In 2 dimensions, it turns out there's only 5 Bravais lattices: oblique, rectangular, rhombic, hexagonal, and square. Even a lot of times we're going to model 3D devices and only really account for 2 dimensions in one plane. We're going to be doing this in a technique called rigorous coupled wave analysis. For another technique we're going to learn, plane wave expansion method, we're going to go look at the 3D Bravais lattices. But for a lot of techniques, we're only looking at the symmetry in the cross section, in which case we only have 5. Okay, so now we know a little bit more about what ways things can be periodic. Now let's start putting some math behind it. So there's a label called primitive lattice vectors, or just lattice vectors. So if we imagine an arrangement of spheres, a lattice vector is simply a vector that takes you from one sphere to the next. It can be adjacent spheres, or it can be a sphere all the way at the other end of the lattice that's thousands of unit cells away. All of them are lattice vectors. The primitive lattice vectors are the shortest possible ones, so they're connecting adjacent unit cells. So of the primitive lattice vectors, there's two types. There is what we call on the left the axis vectors, which point along the edges of the unit cell, and the unit cells being the thing that we would repeat to make the overall lattice. So the axis vectors are very intuitive. They tell us the size of the unit cell, its orientation, very intuitively. But it turns out they're not as useful because they don't uniquely describe the unit cell. For example, all of the cubic unit cells, simple cubic, body center cubic, face center cubic, all of those have the same axis vectors. So we cannot uniquely describe a unit cell. The other type of lattice vector is what's called a translation vector. These do uniquely describe the unit cell. However, given the translation vectors, they're not as intuitive to look at. They're not as intuitive to see the size of the unit cell or the orientation, but they do point to adjacent points in the unit cell, and they do uniquely describe the unit cell. So we will always use translation vectors, but not lattice or not axis vectors. So we have a good idea of what the primitive lattice vectors are. They are the smallest possible choice of lattice vectors, and they of course connect adjacent spheres, if you will. But a lattice vector in general can connect any sphere to any sphere. The important thing here is that the overall translation vector has to be some integer combination of the primitive lattice vectors. If I can't go from any one sphere to any other by some integer combination of the primitive lattice vectors, something's wrong. The lattice is not periodic, or we've chosen the wrong translation vector. Something's wrong. But we should be able to get from any one sphere to any other sphere in the entire lattice just through some integer combination of those translation vectors. So we would call this overall composite translation vector just a lattice vector. It's not primitive anymore because it's really big, but it is still a lattice vector. Then there's a weird concept called the reciprocal lattice. Let's see if I can get my laser pointer working here. There we go. So what is intuitive and what's programmed into your mind is what we call the direct lattice. This is the thing that you can touch. If you manufacture a unit cell or a lattice and you're touching it, you're touching the direct lattice. And it's described by these three lowercase primitive translation vectors. And in this case, they're pointing along the edges of what we'll call the primitive unit cell. We'll talk about that in a little bit. But this does not have to be 90 degrees. These can be oblique and at other weird angles with respect to each other. So what we can do, we can pair off two of these vectors. Let's take T1 and T2. These two vectors define a plane. So I'll outline the plane. This plane repeats throughout the lattice. There's the second plane, which is the same plane, and then there'll be a third one, and a fourth one, and a fifth one. That plane repeats. So given this plane, we can define a whole other vector, and we'll call this capital T3. This vector has to be perpendicular to the face, and it will have a magnitude that is 2 pi divided by the spacing between the planes. Actually, and it's in this perpendicular direction that would define the spacing, not necessarily along this line, but along that perpendicular direction. So two things are conveyed by this vector. It describes the orientation of this plane because it's perpendicular to that, And the magnitude of this is 2 pi divided by the spacing between the planes. Now, we formed capital T3 by pairing together little t1 and little t2. Well, it turns out we can pair this off 3 different ways, and in fact construct 3 different other vectors. These 3 vectors, capital T1, capital T2, capital T3, become the primitive translation vectors of a reciprocal lattice. And here I've compiled them all next to each other. And we have a completely different lattice. This is not a physical lattice. We can't touch this anymore. We're in what people will call reciprocal space, or sometimes they even call it K space. But here we are. We have another lattice, and the capital T's are the primitive translation vectors of the reciprocal lattice. Now, likewise, we could pair these off. If we pair off T1 and T2, these 2 vectors define a plane. We can look at a vector that's perpendicular to that plane, and we can make its magnitude 2 pi divided by the spacing between the planes. If we do that, we're going to get T3, which is one of our original translation vectors for the direct lattice. And likewise, we can pair these off 3 different ways, and we will get our original set of translation vectors of the direct lattice. And we can go back and forth all day. Every direct lattice has a reciprocal lattice, and it's a unique transform. So the reciprocal lattice is not a physical lattice, but it is very useful mathematically. So if your direct lattice has simple cubic symmetry, the reciprocal lattice has simple cubic symmetry. If your direct lattice has body-centered cubic symmetry, then the reciprocal lattice, in fact, is face-centered. So if your direct lattice was then face-centered, obviously the reciprocal lattice is body-centered, and a hexagonal lattice, the reciprocal is hexagonal again. So given the vectors, we can use these equations to pop back and forth, calculate the reciprocal lattice vectors from the direct lattice vectors, or vice versa. Now, everything we talked about with the translation vectors of the direct lattice still apply to the reciprocal lattice. We will have 3 primitive reciprocal lattice vectors. We can form a reciprocal lattice vector that is not primitive, but it has to be an integer combination of those primitive reciprocal lattice vectors. So now let's define something called a grating vector K. So if we have material properties that repeat, and let's say our dielectric constant forms planes, where we are going to have a plane of high dielectric constant, and in between there a plane of low dielectric constant, and let's say that repeats itself. We can define a vector that's perpendicular to those planes and whose magnitude is 2 pi divided by the spacing between the planes, and we will call that a grating vector because that describes this grating. It maybe doesn't describe the magnitude of the dielectric constant, but it describes its periodicity. And so this crazy way of saying 2 pi divided by the spacing, that is useful because we can construct this grating just simply by saying cosine of capital K dot R, where R is position. So K dot R, and that's why we have this crazy definition of 2 pi over the spacing. It lets us do this to describe the grating. So K doesn't tell you how much the dielectric constant is swinging or if it has an average value. Those numbers have to come otherwise. This K just describes the periodicity of the grating. Now, we just described a grating vector, which was perpendicular to the grating planes and had a magnitude 2 pi divided by the spacing between the planes. That's exactly what a grating vector was. That's exactly what a lattice vector was, a reciprocal lattice vector. We paired off our direct lattice vectors, formed planes, and calculated reciprocal lattice vectors from that. which were perpendicular to the planes with a magnitude 2 pi divided by the spacing between the planes. So reciprocal lattice vectors and grating vectors are the same thing. And there's a very intimate relationship between here and also wave vectors, which are perpendicular to the planes of an electromagnetic wave. And they also have a spacing 2 pi divided by the wavelength. So there's a very intimate relationship here. So very often we will analyze periodic structures in reciprocal space because of that. The math actually becomes easier. If we can swallow this whole reciprocal space thing, things actually become much easier. As a quick aside, we're not going to really use this, but Miller indices really are reciprocal lattice vectors. If you pull off the integers from a lattice vector in reciprocal space, those integers p, q, and r, those would be your Miller indices. So I just wanted to make that connection, but we're not going to talk in terms of Miller indices in this class. Next, we want to talk about the concept of a primitive unit cell. We know intuitively, and I've probably heard it along the way, a unit cell is that it's like a tile in a pattern. If we can take that unit cell and stack it onto itself, and if by doing that we construct the overall lattice, we have a unit cell. Adding a little bit more rigor to that definition, we have to be able to stack that unit cell without any overlaps and without any gaps. So they have to fit together perfectly to fill the volume. Then we have a unit cell. So ignore the yellow regions here. What you're looking at are what will be called the conventional unit cells, the ones that make pretty pictures. But it turns out those aren't the smallest primitive unit cells. And when we are modeling, it's very important to figure out what the primitive unit cell is, because if it's smaller, we have to do less calculations, and that's really important. We certainly can analyze the full conventional unit cell, but if we can halve the size of the problem, then that probably means the number of calculations come down by 4 times or something like that. So it's very much worth our while to minimize the size of the unit cell. So we're going to define the primitive unit cell as the region of space around one of those spheres that is closest to that sphere than any other sphere in the lattice. So we're looking at this center sphere. This yellow region is that region of space closer to this sphere than any other sphere in the lattice. And so this yellow region would be the primitive unit cell of a body-centered cubic lattice. Over here for simple cubic, the primitive unit cell and the conventional unit cell are the same thing, so we don't have to worry too much about that one. Here's a face-centered cubic conventional unit cell, and here is the region of space closest to the center sphere than any other sphere in the lattice. And it's amazing to see how much smaller that primitive unit cell is than this conventional unit cell. So clearly we're doing a whole lot fewer calculations in the primitive unit cell than we would be in the full-blown conventional unit cell. So that's the utility of it. Now we have this thing called a Brilluoin zone. So we have a direct lattice and a reciprocal lattice. We figured out how to determine the primitive unit cell for the direct lattice. If we do the exact same procedure to determine a primitive unit cell, but do it in reciprocal space, we're constructing what will be called the Brilluoin zone. So now we have our unit cells, and very often there's even additional symmetry. So for example, here's our unit cell of a square lattice. Here's the outline of it, and there's a sphere in there. But notice this also has left-right symmetry. So in fact, rather than calculate the field throughout this entire square, we really probably would only have to know it in half. And just mirror image those electric and magnetic fields, and we would know the field on the left side. So it has up-down symmetry and left-right symmetry. So in fact, we only need to calculate within a unit cell, or I'm sorry, within one quadrant of the unit cell. Then this circle also has rotational symmetry. If we turn this unit cell 90 degrees, we have the same unit cell back. So in fact, we really only have to calculate the field in 1/2 of one quadrant of the unit cell, and we will know the field everywhere. These things are really, really important when we're trying to minimize the number of computations. So, if we construct the unit cell on the reciprocal lattice, that gives us our Brilluoin zone, and then we apply the concepts we just talked about in the last slide, that there may be additional symmetry. We can whittle down our primitive unit cell down to what we'll call the Irreducible Brillouin Zone. Not the full Brilluoin zone, which is the full primitive unit cell in reciprocal space, but we can potentially exploit additional symmetry and whittle it down to what's called the Irreducible Brillouin Zone. That is the smallest volume of space in the Brillouin zone that still fully characterizes the lattice. Now, if your unit cell is very crazy and there is no symmetry, then the Irreducible Brillouin Zone and the Brillouin Zone are the same thing. Okay, so that's all the lattice vector theory. Now we want to talk about electromagnetic waves inside periodic devices, and hopefully we can find some simplifications to help us. The first concept to understand, I'm showing a dielectric object here and a wave passing through it. When a wave enters some kind of material, it slows down. So it makes sense that the wavefront on the other side will be perturbed a little bit. The part that passed through this dielectric circle is behind. It's behind in phase. It's also called being retarded. But the point is that it's been perturbed by that object. And notice it kind of has the shape of that object. So this conclusion's huge. If I now have a periodic arrangement of those dielectric circles, and I let a wavefront pass through that, notice the wavefront now has the same perturbations with the same period as the structure that it passed through. The huge conclusion is waves in periodic structures take on the same periodicity as their host. They're going to have the same period. They're going to have the same symmetry. Symmetry being, if it's in a face-centered cubic lattice, the field will take on face-centered cubic symmetry as well. So that's a huge, huge thing. So just by looking at the lattice, we're going to know what symmetry that field has already. So now we come to what is called the Bloch Theorem. And in fact, the electric field inside a periodic structure has two parts to it. It has an amplitude portion and this plane wave phase looking term. So this is the total electric field equals some amplitude envelope times a plane wave phase term, if you will. So I like to describe it this way. The overall electric field in a periodic structure looks like a bumpy plane wave. We can decompose this into an amphloid envelope, so these will be the bumps, if you will, and then we have this plane wave looking thing, and the product of the bumps and the plane waves gives us our bumpy plane wave. Now, we said in the previous slide, we said something slightly incorrect. It's not actually the overall electric field that has the same symmetry as the device it's in. So this E does not have that same symmetry. It's actually this amplitude term. That's the thing that has the exact same periodicity, same period, same symmetry as the structure it's in. This plane wave term doesn't have any of the symmetry of the lattice that it's in. And the overall field is the product of the two. So we have a bumpy plane wave, and it's the bumps that take on the same symmetry as the device it's in. So we're going to use this a lot. It's called the Bloch Theorem. So if a device is periodic, we can look at its dielectric constant, where r is position. We can add to that any lattice vector, not necessarily primitive, can be anything. So this vector is going to take us from one sphere to any other sphere. If this truly is periodic, we're going to be back at the same point again as if we did not add this lattice vector. So this is how we're going to mathematically describe our periodicity and symmetry of our periodic structures. And this T, remind you, can be any lattice vector. Doesn't matter what P, Q, and R are, they just have to be integers. They can be negative or positive. Now, if it was that amplitude term that actually had the same period and symmetry as the structure it's in, then our A term has to follow this same rule. And in fact, it does. It must. So it's not that phase term, that plane wave looking phase term. It's not that term. It's this term, the amplitude term, that has the same symmetry and periodicity as the structure that it's in. So many devices are periodic just in a single direction. So here's mathematically how we would write that. Here's our dielectric constant as a function of x, y, and z. But in this case, we're just going to add an integer multiple of the period in the x direction. And likewise, we can do the same thing with the amplitude term of the electric field. Or in shorthand, since nothing interesting is happening with y and z, we can just write our periodicity conditions for one-dimensional periodicity this way, where we're just adding an integer combination of the period in x. Okay, so the whole conclusion there, waves in periodic structures take on the same symmetry and period. And in fact, we express the electric field as an amplitude times a plane wave looking phase term. It's the amplitude that actually takes on the same symmetry and periodicity. Now we're equipped to start talking about electromagnetic band diagrams. So we have Maxwell's equations. We substitute one curl equation into the other, and we derive a wave equation. And that's what I'm showing in the middle. So we're going to put a black box around this. We'll discuss this later, how this is actually numerically solved. But suppose we can solve this as an eigenvalue problem and not worry about how that's solved right now. What this means is we think of an eigenvalue problem as a test. And if I have a guess as to what the magnetic field looks like, I can take the curl of it, divide by the dielectric constant everywhere, and take the curl of that again, and get my magnetic field back again, scaled by a constant, then that means however I came up with that guess is a valid solution for the magnetic field. Now, the magnetic field has to follow this rule, so we don't have all possibilities for electromagnetic configurations. There's only certain ones. So the eigenmodes are those certain configurations of the magnetic fields that would exist in whatever the system is described by the epsilon r, the dielectric constant. And when we solve a mode, we really come away with two things. We have what the mode looks like, the picture of the mode, but in fact for band diagrams we don't use this at all. We also have the frequency of the mode, and in this case that comes out in terms of the eigenvalue, which is k0 squared, and this really is frequency. It's k0 is 2 pi over the free space wavelength. Since we said it's the free space wavelength, that's 1-to-1 with frequency, so we can think of k0 as frequency instead of wavelength. So what information does this model need? Two things. We need to know what the unit cell looks like. We're showing that in green here. So this obviously changes with position, so this epsilon r is a function of position. So that's the first bit of information. We need to describe our unit cell. The second thing is, we're interested in a wave traveling through this. So the question comes up, what direction wave are you interested in? And what is the wavelength of that wave? So just like we did with wave vectors, we can lump that into a wave vector. We're calling it beta here. But beta is perpendicular to the wave fronts, if you will. It's also directly in line with the direction the wave is moving. And it has a magnitude 2 pi over the spacing or the period of that wave. So these are the two pieces of information that we're going to feed this eigenvalue problem solver. What the unit cell looks like, and this wave described by the Bloch wave vector beta. Okay, so now we have our extended lattice. That's what it might look like. Here's what a unit cell might look like. From there, we can construct the Brillouin zone, and then we can further construct the irreducible Brillouin zone by taking advantage of additional symmetry. Now, we're going to label the vertices of the irreducible Brillouin zone with letters. And in fact, there is a convention here, and I will forward you a PDF file with that convention. But these are called our key points of symmetry. Now what we want to do to completely characterize this unit cell, we would have to iterate through this entire volume in the irreducible Brillouin zone and solve the eigenvalue problem to figure out what the field looks like and what frequency those modes are. That's very time consuming, and 99% of the time we don't need all that. What we can do that's much faster and still give us 99% of the same information is to pick a path around this irreducible Brillouin zone. So here's the irreducible Brillouin zone again. We're going to pick a path. We're going to start at U. We're going to go down to X, up to gamma, over to L, down to K, over to W, and maybe even back to U. So here's our path around that irreducible Brillouin zone. Then we're going to take this single line path and stretch it out. And this stretched out becomes the horizontal axis on a band diagram. So if you've ever seen these before in your books and saw these crazy letters and didn't really know what was happening, that's what the horizontal axis is. So as we move across the horizontal axis, we're doing two things. We're changing the magnitude and direction of this wave vector beta. As beta becomes smaller, we're talking about a long wavelength. As it becomes bigger, we're talking about a shorter wavelength. Notice between gamma and L, we're going outward in the unit cell from gamma to L. So the direction of that wave's not changing. So what we're actually doing by moving from gamma to L is saying the wavelength is getting shorter and shorter. At gamma, the wavelength is infinite, so we're at DC essentially, and then we go all the way up to L, in which case the wavelength is going to be its shortest there. Then as we go from L to K, the magnitude of the wave vector probably changes a little bit, but for the most part we're only changing direction now through the lattice, going from L to K. So anyway, you can work through this and you can see that we're changing the direction and magnitude of the Bloch wave vector. If I was going to way oversimplify this, I would say think of the horizontal axis in a band diagram as just direction through the lattice. So we're spanning a whole bunch of different directions because the wave, depending on what direction it's going, could potentially behave differently. So what we're going to do is we're going to set up a loop, a for loop, and this happens way later in the course. But we're going to set up a loop. We're going to probably pick about 200 points along this horizontal axis. So we're going to go one at a time. One at a time, one at a time. For each of those, we're going to calculate all of the modes that would exist in that lattice. And so we get a bunch of those, a bunch of different frequencies. And so given our Bloch wave vector, we're going to go up here and plot as a single point all those different frequencies. Then we're going to move to the next Bloch wave vector and plot all those frequencies. Well, all these dots line up to form bands, and that's what we're showing here. These are the bands. And it's really a tally of all the possible electromagnetic modes that can exist in that lattice. In semiconductor theory, they would probably call this energy. So this is a map on the horizontal axis of direction through the lattice, and then going vertically, all the different frequencies that have a mode with this same direction and period as the horizontal point on the plot. So that's what a band diagram is and how it's constructed. I'm not going to be able to play it with this slideshow presentation, but I will play this movie in class, and you'll see a blue vector over here. You can watch that iterate or bounce around the irreducible Brillouin zone, and as it's moving through the irreducible Brillouin zone, I'm plotting all of the modes that are in the lattice, and then they all line up to form bands. Unfortunately, I can't play it here with how I'm recording the slides. So, because we've chosen a straight line path around the Brillouin zone, there's definitely a possibility we're missing information, but it is very, very fast, orders of magnitude faster than if we had to solve that eigenvalue problem at every point within that irreducible Brillouin zone. So it's very fast and rapid, and it turns out we can get a lot of information from that band diagram. There are things called band gaps. These are spans of frequency where there are no bands, and we'll see that in an upcoming slide. And the lattice acts like a mirror throughout within these bands. There are no electromagnetic modes. Nothing will propagate through the lattice in those band gaps, and so it acts like a mirror. Where there is a lot of bands all bunched together, that's where the lattice probably transmits pretty well. So we can look at little spans of frequency where we think the transmission is going to be high. Clearly, if there's a band gap, transmission is going to be low. We can also discern phase velocity from the slope of the lines. Phase velocity is the apparent speed of the wave if you're looking at the phase. Group velocity is the actual speed at which energy or power is moving through the lattice. And we can also look at dispersion. Dispersion is any time that different frequencies behave differently. So different frequencies may travel through the lattice at different speeds or other craziness. So anything like that is called dispersion. This is a very, very busy graph. So we'll take this one step at a time. So I started off with a periodic structure, and I probably stacked about 10 unit cells together and calculated the transmittance through that. So these dips mean the lattice is reflecting within those bands of frequency. So this is just a very easy to follow transmittance curve. This is the more confusing band diagram on the left. The solid blue lines are the bands of this periodic lattice. And notice that there's two different dielectric constants here, two different refractive indices. If I averaged those and made a homogeneous unit cell, and then calculated the bands from that homogeneous unit cell, I would get these green dashed lines. And very often these are called the light lines. But they're in the perfectly homogeneous lattice. There are no high or low refractive index regions, and really nothing interesting happens. But we can compare those light lines to the bands we actually get. And what we can see at the gamma point, notice these two lines are virtually the same, the light lines and our bands. That's because the wavelength is so huge that we really are just seeing the average refractive index in the lattice. So it makes sense those lines would be similar. Now, as the period of our Bloch wave vector gets larger and larger, so we're moving from gamma to y, at some point the wavelength becomes short enough that it starts to interact with the lattice. The wave starts bouncing around and resonating, and crazy things happen. That's when the band pulls away from the light line, because there's more physics happening here. So anytime your band pulls away from the light line, like right here, that is dispersion. Okay, now let's look at band gaps. If we look at these lines, what I see is there's this range. If I look at the bands, I see there's a range of frequencies. I can go all the way across, and there are no bands. That is called a band gap. So we certainly would definitely see a dip in transmission in this band gap. But notice this is actually wider than that. Why is that? Well, if we're calculating transmittance, we're probably only calculating that for a single direction through the lattice. We're not testing all possible directions. So that's what's happening here. We're really only looking at Bloch wave vectors in this range. Actually, I should say from gamma to x. So if we look at the band gap, if you will, in that region, it is much wider and corresponds very well to this. Likewise over here, we see we have a second gap in the bands, a band gap. But our simulated gap is wider because we're only going one direction, and really it's more closely associated with this one. And up here, and the same story at the top. We have a very, very narrow band gap, and we just see a weak little dip in transmission. So we can look at the band diagram and know where the lattice is becoming dispersive. We can make pretty good guesses where it's not going to transmit, where it is going to transmit. Now let's look at phase velocity and group velocity. So we have phase velocity. If we take a line from the gamma point to wherever we're interested in the phase velocity, the slope of this line, the red dashed line, that is phase velocity. Then if we look at the slope of the curve at that point, that's our group velocity. So phase velocity is the apparent speed of phase. So if we're looking at the wavefronts, they appear to be moving at a certain speed. And the group velocity can be different. Now notice, if we were interested in down here, if you think through it, phase and group velocity are going to be the same here. It's only when the band deviates from the light line that group velocity and phase velocity differ. So we can conclude it is dispersion that leads to group velocity and phase velocity being different. Anyway, there's a whole bunch we can interpret in photonic band diagrams. This class, we're not going to concentrate so much on interpreting that. That's going to be for our next class, and we'll talk about this all over again if you choose to take my follow-on course to this. But we are going to be calculating these things in this class, and I think it's nice to know what it is you're calculating and why we're calculating it. Okay. So I hinted to this before, but if we're marching around just the perimeter of the irreducible Brillouin zone, we are potentially missing information. So if we were just calculating the band diagram of this two-dimensional lattice, we're probably going to go from gamma to x up to m and back to gamma and march around this irreducible Brillouin zone. Well, in fact, there may very well be some interesting things happening right in the middle. And if all we're doing is going around the outside, we're completely missing that. But it's said somewhere that the band extremes almost always occur at the key points of symmetry. So if we're just looking at band gaps and things like that, it's a pretty good thing to do just to hit those key points of symmetry and everywhere in between. However, we are missing information, and there's always that small chance that we're missing something interesting. Maybe there is even a band extreme off of the Brillouin zone. One of these days I'm going to look up a case where that is true, and I'll share that. So, imagine now, here we have a full Brillouin zone, and we're not going to care about the irreducible Brillouin zone. We're not going to care about just going key points of symmetry. We're going to go point by point, and we are going to fill in this entire area and calculate the modes and frequencies of every mode throughout the entire Brillouin zone. So this bottom plane is going to be our Brillouin zone, and every combination of beta x and beta y, we're going to plot our frequencies. And in fact, they would keep going up, but I'm only showing 3. So if I iterate through here and do this for a lot of points as I'm showing, what you'll see is we have our bands now, but in fact they're sheets. They only look like lines before because we just took a single line path around the Brillouin zone. If we fill in every point, we get these sheets. This is actually the complete band diagram, and if you want 100% guarantee that you're not missing anything, then you need to calculate the complete band diagram that we're showing here. This brings us into the topic of index ellipsoids. So remember what these are. We talked a little bit about them the other day. These are surfaces that essentially characterize the refractive index of a lattice in any direction the wave is going. So if we pick a point on the surface and we start at the origin and create a vector that points to that point on the surface, that vector is our K vector, and it has a certain magnitude associated with it. Well, in most materials, the magnitude of your K vector is the same thing no matter what direction it's going in. So that means refractive index is the same in every direction. And the equation that quantifies that is called the dispersion relation. And in this case, it forms a sphere. In anisotropic materials, these actually now become true ellipsoids. They can look like pills or bullets or things like that. And it gets even crazier for biaxial materials. Suffice to say that the shape of those index ellipsoids can be non-spherical and can be other crazy shapes. We talked about the point connecting the origin to that point on the surface being the K vector, describing how phase propagates, but power propagates in a direction normal to the tangent of the surface. So when your index ellipsoids are circles or spheres, K and P are in the same direction, and in fact this is how we're programmed to think. But as soon as it's not circular or spherical anymore, the direction of phase and power can be very different. So how do we calculate these? Let's go back to these sheets that we had. Now imagine I'm taking this green sheet, drawing it continuous and smooth over here. So now imagine I choose a plane at some value of A over lambda. So imagine I choose a plane where it slices through that, forms an isocontour, if you will. And here I'm showing three different planes, how they slice through this, what the isocontours would look like. And in fact, these isocontours are the index ellipsoids. And we choose one frequency to give us one index ellipsoid. So if we chose a frequency of, I guess that's probably 0.75, the index ellipsoid would look like this. It actually looks very square. So using this algorithm of solving Maxwell's equation as an eigenvalue problem, we can actually now calculate these index ellipsoids. So here's a whole bunch of sheets from some unit cell, and I take the first band and I slice it again, and what I see is I have very circular, at least at the really long wavelengths, I have very circular isocontours. So this means nothing interesting is happening. No matter what direction the wave is going, it sees the same thing, and this is kind of what we said before. When we have a very, very long wavelength, it's really just seeing the average. The wave isn't really reacting with or resonating in the lattice yet. Now that does happen when we get to the outside. There's a little bit of craziness happening, and that's when the wavelength is approaching the same periodicity as the lattice, and we start getting resonances established and other crazy things happening. So if we looked just at those isocontours, this would be our lattice. And if we look just at them, we would see a plot like this. And we are looking straight down onto our index ellipsoids. And the index ellipsoid changes with frequency. And the number that I'm writing over top of that, that is the frequency of those isocontours. And in this case, frequency I've scaled as the lattice spacing divided by wavelength. But since it's 1 over wavelength, that really does make it a frequency. And we can go from our k0 squared eigenvalue to this frequency very easily. It's just a constant. So that is it for this presentation. The band diagram stuff was kind of a bonus. We're not really going to be interpreting those in this class, but I just wanted you to have an appreciation of why we would calculate these things, and also how it ties into these index ellipsoids. The most important thing to come away with this lecture are the lattice vectors, the symmetries, and the Bloch theorem of what that means. It really means it's just the amplitude of the electromagnetic waves that take on the same periodicity. But there's also this plane wave looking phase term that does not have any symmetry. It has its own thing. And the overall electric field is the product of those two. And so electric fields in periodic structures look like bumpy plane waves. And you will see plenty of pictures of that. So that's it for this lecture.